Thanks for watching today, Physics 1 class. We are going to talk about Chapter 9, Momentum. This is the last chapter that we're going to be doing before we take the final. So, let's get right to it. This video is going to be about primarily the concepts in Chapter 9, but we'll also do some calculations when it's a convenient time, or to illustrate some of the principles that we're talking about. We'll work with the equations in class when we do some problems together. So, Chapter 9, we're going to talk about conservation of momentum. Here this is an octopus which sends out jets of water to propel itself. The momentum of the octopus plus the water system stays the same. The momentum is conserved. So momentum of the system does not change, but as it expels water out behind it, then it gets an increase in momentum. The water is moving away from it, so it shoots water out this way, and then it pushes the octopus forward. Okay? So we're going to look at before and after problems. So we'll look at our initial momentum of two objects usually, and then we'll look at after some event. All right, so we're going to take a look back at Newton's third law. We learned about in Chapter 4 that we will apply Newton's third law, which states that the force that object B exerts on A has equal magnitude but is directed opposite to the force that A exerts on B. So when these two things are pushing against each other, when any two things push against each other, they exert an equal and opposite force. So if I were to go push on my wall, or if I push on my head with my hand, well, my hand exerts a force on my head, but my head exerts an equal and opposite force back. Okay, so a hammer hits a nail. The force of the nail on the hammer is A greater than the force of the hammer on the nail, less than the force of the hammer on the nail. C equal to the force of the hammer on the nail, or D 0. Well, we just saw that Newton's third law said that they have to exert an equal force on each other. So we're going to pick C here. They exert equal and opposite forces on each other. So when the hammer hits the nail, it exerts a force, but the nail also exerts the same force back at the hammer. Okay, so here are some questions from the reading. What is impulse? Impulse is A, the force that is applied to a random time. B, a force that is applied very suddenly. C, the area under the curve, the force curve in a force versus time graph. Or D, the interval that a force lasts. Well, the way that you find it is by finding that area under the curve of your force versus time graph. If you can estimate that, that's going to give you your force. So it looks something like this. Okay, so in my force versus time graph, so I'll draw a graph like this. Okay, so this axis up here is my force, and this is my time graph. Okay, and as the force is applied, okay, if I want to find the impulse, then I need to find the area under that curve. Okay, now if the time is short, okay, then my force is going to be higher. Okay, and if we want to, so this is the higher curve up here. Okay, So if we want to minimize the force, then we can increase the impact time here. That's how we would do it. Right? That could make things safer if you were in an accident, things like that. Okay. Next question. In the impulse approximation, a large force acts on for a very short time, or B, the true impulse is approximated by a rectangular pulse. Well, we could approximate it that way. C, no external force acts during the time that the impulse force acts. Or D, the force between colliding objects can be neglected. The correct answer is A, a large force acts for a very short time. Okay, so the impulse approximation says that we can ignore smaller forces. So for example, if you have when two objects interact, we can ignore small forces. So in the case of a bat and a baseball, the weight of the baseball is about 1.5 newtons, whereas the force from the bat is about 30,000 newtons. So that means we can effectively ignore smaller forces like drag during this interaction time because they're so much smaller. Right afterwards or before the collision, then you can't ignore those things. But the impulse approximation says that during the collision, we can ignore smaller forces. Okay, the total momentum of a system is conserved. A, always. B, if no external forces act on the system. Or C, if no internal forces act on the system. Or D, never. It's just an approximation. Well, we can't always ignore it, because if an outside force acts on the system, then there's going to be a change in the momentum. But if no external forces act on the system, then momentum is indeed conserved. So wind resistance, things like friction, those will affect your system. They'll change the momentum, and so momentum would not be conserved. If it's isolated and you could ignore those, then it's okay. We can treat it as conserved. So in an inelastic collision, impulse is conserved, A. B, momentum is conserved. C, force is conserved. Or D, energy is conserved. Or E, elasticity is conserved. Well, impulse is, that's hard to really understand what impulse being conserved means. But B, momentum is conserved. So an inelastic collision is when two things stick together, right? And in that case, then you would treat, you take the momentum of the particles before, and it has to equal the momentum of the particles afterwards. But then they're effectively stuck together. Okay, so an object's angular momentum is proportional to its mass, moment of inertia, kinetic energy, or linear momentum. Well, it is moment of inertia, but we haven't really talked about angular momentum. Suffice it to say that if something is spinning, it will keep spinning, and it will continue to do so unless a force acts upon it, which would change its momentum. But we haven't talked about angular or circular motion. Okay, let's start with 9.1, impulse, right? And if you haven't watched the video in the book, there's a great video that talks about impulse, where they kick a giant squishy soccer ball, and you should definitely watch that. It's in point 9.1. Okay, so collision is a short duration interaction between two objects. When you kick the soccer ball here, those two objects are connected for a brief time. They're together, and this is what's happening during the collision, when those two things are in contact with each other. And that duration depends on the materials. So for squishy materials, they're in contact longer, so the collision is going to be longer. For harder materials, the interaction can be much shorter, which is why when you crash, you would rather have squishy foam on your dashboard instead of hard metal. Because remember, when a car crashes, okay, there's the collision with whatever the obstacle is. But then if you're not wearing your seatbelt, you are going to have another collision inside of your car where you hit the dashboard. And if the inside of your car were made out of metal, the collision time would be very short, and so the force would be very high. So you want squishy foam to increase that time of the collision. So you will get hurt less because you will experience less maximum force. So when kicking a soccer ball, the foot first contacts the ball, the force starts at 0, then quickly rises to a maximum value, then quickly falls back to 0. The force is applied only when the ball is in contact with the foot, and the impulse force is a large force exerted during the short time interval. So before that soccer ball hits your foot, there's no force. After it leaves your foot, there's no more force. Then it's just flying through the air. But here, this is the time when the foot is in contact with the ball. When your face is in contact with that squishy foam on your dashboard, or maybe the airbag in your car. So you want to increase that maximum time. A harder kick, a larger maximum value, for a longer duration, right, or a wider force curve causes the ball to leave the foot with a higher speed. Okay, the effect of an impulsive force is proportional to the area under the curve versus the time curve. Okay, so if we want to know what our impulse is, we need to find the area under the curve. You can do that by kind of approximating it as a curve. Okay, the area under both of these forces is the same, thus both forces deliver the same impulse. This means that they have the same effect on the object. The area under the rectangle is the F average delta t. Its width is delta t multiplied by its height. Okay, so if we take our average force there, we can get the same area by making it into a square, which is much easier to find the area under the curve than something like this. Okay, and you could use calculus to do this, and you learn a lot of ways to find the area under the curve in calculus. If you knew the function, you could integrate and find the area under the curve. But that's if you're using calculus. 2 1 kilogram stationary cue balls are struck by cue sticks. The cues exert the force. The force is shown. Which ball has the greater final speed? Okay, well, we need to consider the area here. What is the area under the curve? Because the one with the greatest impulse is going to have the highest final speed. So here I see the maximum force is 100 and its width is 2 microseconds. Here this is 20 microseconds and that one is going to be 10 newtons. So 10 times 20 is 200, and over here 100 times 2 is also 200. So if you determine that the area under the curve is the same, then the balls are also going to have the same final speed. Right? All right. It's useful to think of the collision times in terms of the average force. The average force is defined as a constant force that has the same duration delta t and the same area under the curve. Okay, said that. Okay, so impulse J, we always use J for impulse, is the area under the curve. Impulse due to a force acting for a duration of delta t. That force is your face with the dashboard pushing on your face during that collision, the airbag pushing on your face. And by the way, airbags do have a pretty high force, okay, because it can break your nose. You're not going to look good after you get hit in the face with an airbag, but it does decrease the forces significantly, so you won't die. You might have a broken nose or black eyes, but you won't be dead. That's what they're going for. So impulse has units of newtons times seconds, but that's equivalent to kilograms times meters per second. Okay, and kilograms times meters per second, that is the units of momentum which is mass times velocity, or kilograms times meters per second. Okay, so the latter are the preferred units of impulse, and the impulse is a vector quantity pointing in the direction of the average force vector. Okay, so that's the force exerted on your face by the dashboard. Okay, and it's pointing away from the dashboard. It's putting force on your face. Yes. All right, finding the impulse on a bouncing ball. Figure shows the smooth force versus time data for the bounce of a rubber ball. What is the impulse on the ball, A, and what is the average force on the ball? Okay, well, the impulse is the area under the curve. Okay, so we just need to find what the area of a triangle is, and we can do that. So if we cut this in half here, that's about 4, and then we go up here to 300 newtons. So we could take half of that and put it on the other side. So let me draw a picture of what I am talking about. Okay. So here's our picture. Well, we got this picture over here, and I can take this. So I will draw a similar graph right here. There we go. Oh, I'm not drawing straight. There we go. All right, so this is 800. Right? We can cut that in half. Say 4 milliseconds. Okay, so right there. Move my head. There we go. Move my head over here. All right, so we have a basically a triangle here. That's half of what we had. Try and draw it at the same scale. Okay, so there's half of our triangle from over there. Well, we could just take that other half and stick it up here, turn it upside down, and then put it right here. Okay, so this is basically a square. So 4 times 300 newtons right there. So 4 times 300 newtons. That's going to be our the impulse under the curve. Then the average value of a square is right here in the middle, so that's 150 newtons. And I did that with just a picture. Okay, so I took that other half, stuck it over here, and so from this triangle there, yes, this one, I'm pointing at this triangle, then I took half of it and I stuck it here. Yeah, right over there. See? So I took this one and I put it here. So see, I took it here and I put it there. Oh man, what am I even? There we go. Oh, see, now I can put my finger in the triangle. There it is. I took this half and I set it there. Ka-chunk, right there. Ka-chunk. What are you even doing, Dr. Wisby? I don't even know. Okay. Well, we're just going to skip ahead here. Let's see what the answer was. Did we get it right? Yeah. 150 newtons. They did it with an equation. I did it with pictures. What did we get there? Did we get the right? Yeah, 4 times 3. Okay, that's going to give us 12 kilograms times meters per second. 4 times 3. Can't beat that. We did it with the square here, just with pictures. Yeah, way better. Okay, moving on. Our experience tells us that giving a kick to a heavy object will change the velocity much less than giving the same kick to a light object. We know that. You know this. That's what the guy always says in the videos in the book. He's like, you know this. Huh. I don't have a blue shirt, so it's not as creepy. Or maybe it is creepy. Okay. I'm not saying that is creepy. Oh, I'm really quiet now. Our experience tells us that, yeah, I heard that. We want to find a quantitative relationship for the mass, impulse, and velocity change. Hockey puck. You hit it. So it starts going on. While the stick is in contact with the puck, it exerts a force F average on the puck, causing it to accelerate. So we have VI before, VF after, and it was accelerated by this force. So we had a change in velocity due to this force. That's the only way the velocity or the momentum changes, if there's a force acting on it. F equals ma. Let me just write that. If you don't remember anything else from this class, remember F equals ma. Oh, I need a t-shirt that says F equals ma. Oh wait, not F. F-U. Why did I think F-M-U? I'm not going to think about that too deeply. Okay, from Newton's second law, the average acceleration is related to the change in the velocity by the average velocity here equals delta V divided by delta T. Okay, so that's our average velocity. So delta T is our time period, and then delta V is our change in velocity. Okay. We combine these two quantities to find that, yes, F over M equals A, but A equals VF minus VI delta T. This is important. We're not going to watch that video. You can watch the video yourself later. Okay? So now we divide both sides by delta T. Okay? Or we multiply by delta T. Now we get F times delta T. We just took that over. Okay? Because we had delta T here on the bottom. And we switched our sides here. Okay? So what did we do? We had F average, okay, divided by M equals VF minus VI divided by delta T. So I can multiply both sides by delta T and M. Just multiply both sides by delta T and M. Okay, so there we go. Got our equation now. So my M's cancel here. My delta T's cancel here. So now, that's a G. That doesn't. Okay. So now we have, going up here, F average times delta T, right, is going to equal MVF minus MVI. Okay, so now we have this, which we're going to call this momentum. Okay, so J, this is going to be J. We're going to set that, we're going to call that J. That's not, J is impulse, not momentum. And this is going to equal delta P. Okay, so J equals delta P, which is F average delta T. Okay, this is an important equation. You should know this equation. What does it mean? All right. So we end up with momentum is the product of the object's mass and velocity. It has units of kilograms times meters per second. Okay. Momentum is a vector. It has a velocity. Velocity is a vector. So momentum always points in a certain direction. Okay. And it could be an X, Y, or Z. And depending on how you call your coordinate system, then it's going to change accordingly. So you want to pick a coordinate system intelligently so you can eliminate hopefully at least one dimension. So if you can get rid of Z and only deal with X and Y, that's much better. It'd be better if you only had to deal with one dimension. That's even better. So if we can eliminate a one direction, that will make our life easier. Get rid of Z. We don't need it. Okay. So the magnitude of an object's momentum is simply the product of the object's mass and speed. Okay, that's the magnitude, but the direction is important. We're going to see that later. So some typical falling values of momentum. Okay, so for a falling raindrop, the momentum is 10 to the minus 4. Speed is 5 meters per second. Okay, so for a bullet, 500 meters per second, and this gives us a momentum of 2 kilograms times meters per second. A pitch baseball, this has more momentum than a bullet or a running person. Okay, so if you're running, you've got more momentum than the bullet. Even though the bullet's going 500 meters per second, you're heavy. Okay, so you can hit something with a lot more momentum. Or a car on a highway, 3 times 10 to the 4. That is a lot of momentum. So, some of these can kill you. Pretty much, well, all of them can kill you. Maybe not a running person unless you had a spear or something like that. If you had a spear or a pointy object, maybe that's why they always ran into battle with swords, because you do have enough momentum to technically kill someone. So, what's the lesson? Don't run with sticks. Yeah, big takeaway there. Don't run with sticks. See, don't say you never learned anything in this class. Impulse and momentum are related. J equals PF minus P. J is equal to delta P. It's D, or triangle, for delta. Yes. You can have impulse in different directions. You could have a change in momentum in X. You could have a change in momentum in Y. Therefore, you get a change in impulse in X or Y. Okay, impulse and momentum theory. A putter delivers an impulse to the golf ball, changing its momentum. Yes, Tiger Woods steps up to the plate, gives it a big whack. Okay, maybe that's a baseball. Okay, so here's my golf swing. So I got my fingers. My fingers may know it's like this. There we go. I did take a golf class in college, so I know what I can hit golf ball sometimes. I haven't played golf in a while, but I could hit the golf ball. I could actually get off the ground. It's not as easy as it looks on TV, okay? I'm not a great golfer, but whatever. The club delivers an impulse to the ball, increasing the ball's momentum. The club delivers an impulse to the ball, increasing the ball's momentum. Okay, so we get a change in momentum.
Thank you, like and subscribe down below.